Welcome back to Math 451. We're going to pick up where we left off last time as we ended with rational numbers and had talked about whole numbers. We're now going into what we call preliminaries. This is supplemental to your textbook, but we're going to ask if we need anything more than what we have. These whole numbers, both positive and negative, and rational numbers, both positive and negative, are they enough? Well, what we're going to find is that they aren't, and in fact, they even have some oddities that we're going to need to discuss. So rational numbers, are they enough? Let's consider that problem. Can you solve any math problem you want using only whole numbers and rational numbers? Well, I think there's a chance of that. Let's take a look at that possibility. So rational numbers are going to be considered dense on the number line. What do I mean by dense? Well, it means that two rational numbers can become arbitrarily close to each other. You can make two rational numbers as close as you want. So what do I mean by dense? What I mean is that you pick any spacing you want on the number line, and I can find two rational numbers that are at least that close to each other or closer. So it seems as though anything you're trying to account for can be adequately represented using a rational number. Well, let's explore that a little bit and see if that hypothesis of density seems right. Let's say you have two rational numbers, R1 and R2, and you think they're pretty close to each other. The distance between the two is very, very small. Well, let's construct a number right in their middle. In other words, let's create the average of R1 and R2. Clearly, that new average that we're calling R has to be closer to R1 than R2 is, and it is also closer to R2 than R1 is as well. So we have cut the spacing in half of two numbers that we thought were already pretty close. What would that number look like? Well, it's clearly the average of the two is listed there, and I could replace the R1 and the R2 with a ratio of its own, P1 over Q1 and P2 over Q2. If I just do a little arithmetic with some cross multiplying, I end up getting two products that are added together in the numerator, what you're looking at here, right here in the parentheses, and you end up with a product of integers in the denominator. Well, clearly, if you multiply or add any integers together, you end up with another integer. So this is an integer divided by an integer, and therefore it is a rational number. So the average of two rationals is rational and closer to either one of them than you were with at the beginning. And if you would like to continue that and keep cutting them in half, you're still taking averages of rational numbers, and the numbers can get closer and closer and closer until you can get as close to any requirement as you would like. Well, that would tell me that, practically speaking, rational numbers are enough. If you can get arbitrarily close to any solution with a rational number, you ought to be satisfied. And in fact, that probably is a reasonable position to take. But nevertheless, let's go on to ask if there even are any numbers that are neither whole nor rational. And the way you would explore that is to consider a problem for which a solution must exist. So the Pythagorean theorem would say that if you take two legs of a right triangle, if you squared them individually and added them, then that number would be the square of the hypotenuse connecting the two endpoints. So what is x? Is it a rational number? Is x rational? Can you get as close to x as you like using only rational numbers? Well, we've kind of answered that already. The answer is yes, you can. But the equation x squared equals 2 has a solution, and as it turns out, is not rational. How can that be? Can you prove that? Can you prove that it's rational or that it can't be rational? This is what we're going to do, is we're going to face this using what's called a proof by contradiction. So let's go ahead and try to solve this equation, x squared equals 2. We will assume that the solution x is rational, meaning you can represent it by the ratio of two integers. If by making that assumption we discover that we can create nonsense or something that cannot be true, then we reject the original assumption, which in this case is that such a ratio does exist and is still the solution of x squared equals 2. Okay, now we're also going to go back and ask the question we did at the end of last time, and that is it possible for both P and Q to be even? We claimed that wasn't possible, but if you need to convince yourself of that, suppose that it is. You've got P is some multiple 2 and Q is some multiple of 2, and you could divide both numerator and denominator by 2 to reduce the form. Then just continue to do this dividing of numerator and denominator by 2 until one of them quits being even, because you can keep it up as long as they're both even. So that's our argument that either P or Q or both must be odd. Okay, you might wonder, well, so what? Now that you've convinced me of that, what are we going to do with it? Well, let's take a look. So we are assuming x squared equals 2. We have assumed that x equals some p over q, which means p over q squared is 2. That would imply that p squared equals 2 times q squared, which therefore must be an even number, because it's 2 times something. If p squared is even, then p itself will have to be even, because if p were odd, you would be able to multiply it out as I've indicated here and end up with an integer times 2 plus 1, which is an odd number. So if p squared is even, which it must be, so is p. And now we know that one of those two numbers, and in particular the numerator, must be an even number. Well, that means q better be odd, because we've already discovered that q or p must be odd. So it must be q. Well, let's continue with this logic. Since we now know p is even, there must be some whole number m such that p is equal to 2 times m, otherwise it wouldn't be even. So let's write it like that, 2 times some number m. Well, we have the relationship from above that p squared equals 2q squared. I'll substitute my 2m for p, and I end up getting 2 times m quantity squared is equal to 2q squared. And if you just do the algebra, you end up with q squared equals 2 times m squared. In other words, q squared is even. But by the same argument, if q squared is even, so is q. So now we have an issue, because we've just proven that p and q must both be even for a solution to exist, but we've also shown that you can't reduce that to a lowest to lowest terms unless one of them is odd. So you have a contradiction, and therefore it is impossible to create a rational solution to this equation. And thus we've captured our first irrational number, the square root of 2. It turns out the square root of 3 is irrational, the square root of 5 is irrational, and in fact there are so many irrational numbers that they swamp out the rationals. There's even no comparison to the density of irrational numbers as there is to the rationals. Now that's annoying, particularly since I just constructed a rather practical problem for which I want a solution, and I can't use my rational numbers to get an exact result. Now that problem, compounded with the fact that computers, which we would like to use, can only manage rational numbers, we've just created a vast number of problems that can't be solved exactly. And that's the way it is. Okay, so that's one problem. Here's another oddity we have in numbers. If I told you that 0.999 repeating was exactly equal to 1, I think you might not believe me. You'd say no, 0.9 repeating is just slightly smaller than 1. But in fact, they represent the same integer. The integer 1 can be represented in both these ways. Let me prove that. If you don't believe it, we'll take a closer look. Let's let x equal 0.9 repeating, and we'll multiply left and right side by 10. If we do that, we'll get 10x equals 9.9 repeating. Now, there'd be nothing wrong with subtracting the same thing from both sides, so I'll subtract x from the left side and 0.9 repeating from the right, because that's what x is. If I do just a little bit of math, the left-hand side's pretty easy. You get 9x, And on the right-hand side, if you just separate out the 0.9 repeating and reorder things a little bit, you end up getting a 9 plus 0 on the right. Take 9x equal 9 and divide it by 9, and you end up with x equals 1. So there we have it. If you start assuming x equals 0.9 repeating, you can algebraically prove that it is also exactly equal to 1. That gives us a little bit of problems on computers as well. So with this list of oddities and now a little bit of stress over the fact that we've developed a vastly dense numbering system called the irrational numbers that have no way to be represented on a computer, we're going to have to mull over that a bit and see if we can fix that next time.